All right. So the next thing we want to talk about is matrix notation, because very rarely will we leave these systems written like you see them here with your variables x's and your traditional x, y's, and z's in them. Rather, we're going to be converting these to matrices, and that's where we'll be doing all of our work. All right. So of course, a matrix is just this kind of grid of numbers. And when we convert this system to a matrix, all we do is we grab the coefficients like that. And I'm going to stop there for a second. I'm going to put this other bar there. Right there, if we just grab the coefficients, then that is called the coefficient matrix. All right, so this is our coefficient matrix because it just contains the coefficients of the system. However, if we go ahead and take the coefficients and also tack on the right hand side of the system, the right hand sides of the equations, the solutions, or then we get what's called an augmented matrix. Now, there are times we'll use the coefficient matrix, and there's times we'll use the augmented matrix. And in some books, the augmented matrix is written with a dotted line right there to indicate where the equal signs go in the system. But in this book, in general, you're not going to see those dotted lines. All right? They'll just tell you it's an augmented matrix, and you'll know that that's where the dotted lines are, that's where the equal signs are. And if you had to convert this back to a system, you would know exactly how to do it because these are always your x sub 1 coefficients, and these are always your x sub 2 coefficients. Then you have your equal sign. Then you have your right-hand side of the system. So watch for that language. If they say, here's a matrix and it's an augmented matrix, then you know it contains all the information for the entire system, as opposed to just the coefficient matrix. Okay? That will catch some of you sometime, but hopefully now that you know about it, you won't have to worry about that. Now, so this matrix represents the system, and we will use this matrix to solve the system using using elimination. Now, what we can do to this is we can manipulate the rows in this matrix using what are called elementary row operations. All right, elementary row operations. And these are things we can do to the matrix that are legal, okay, and that will result in a different looking matrix, and it will result in what we call an equivalent matrix. So let's just quickly mention what those three elementary row operations are. We'll just write them down. You can get the more details. The first one is replacement. And this is the most complicated, so I'm going to leave that to describe here in a second. Let's talk about the second one. Very simple, interchange. And so you just swap two entire rows. You swap row 1 and row 2 in this case. And clearly, if you interchange the rows, the system it's still the same. It's an equivalent matrix, and so it will have the same solutions. Okay? And then lastly, is what we call scaling, and that's where you multiply all the entries in a row by a non-zero constant. Okay, so positives or negatives, as long as you do it in the row, you're okay. Everything in the row, all the entries in the row. And so you're multiplying everything by a number. But you might say, could I divide? Yes, we can divide if we remember that division is nothing more than multiplication by a fraction, right? So that still works. Now, when we do any of these three changes, we get a different matrix that has different entries, but it's an equivalent matrix in that if we convert it back to systems, that system will have the same solutions as the original system. So just think of the process here. We've taken our system, right? We've taken our system. Let's not erase it. We've taken our system. We've converted it to its augmented matrix. And then we do these elementary row operations to solve the system. And each time we do a row operation, we get an equivalent system, but the solutions have not changed. Okay, so we're looking to change this matrix and get an equivalent system that is easily solvable. And because we've only used these elementary row operations, the solution to this simple system will be the same as the solution to the original system. Now, we've talked replacement, that final row operation. That's where you get to replace one row by the sum of itself and a multiple of another row. Okay, now that's kind of important. We are replacing one row by the sum of itself and the multiple of another row. And we do that all the time. You'll see that here as you work through these problems. But the point is, to be an official elementary row operation, we only get to multiply one of the equations by something, and then we add it to it, or one of the rows by something, and then we add it to another row, replacing that other row. Now, when you solve a system by elimination, so for instance, you may remember, if you want to solve this system by elimination, you would say, okay, I want to eliminate the x sub 1s. Or let's say I want to eliminate the x sub 2s. That's not the easiest, but if we wanted to eliminate the x sub 2s, you'd multiply the top row by 7, the bottom row by 5, add the results, and the x sub 2s would be eliminated. But we multiplied both equations by a scalar. In the official elementary row operation, you don't do that. Officially, what you do is you multiply one row by something using scaling, and then you can multiply the other row by the appropriate thing and add it to the original row. So it's actually a combination of two row operations. Anyway, as you do these operations, you will end up with an equivalent system that leads to a system that is easily solvable. All right, so let's look at this example here, a 3x3 system, and see what it would take to solve this using elementary row operations and some of the notation that we'll use along the way. Now you're going to copy down all of the coefficients and the right-hand sides of the equations. And of course, you want to make sure you've copied them correctly and haven't missed anything. One thing I do to kind of help catch any errors that I may have made is, if I'm writing them down, so when I wrote these down, I wrote them down horizontally, right? When I double check, I'll check them vertically. That just works with my mind to see if I catch any mistakes. So let's just see the elementary row operations that we need to do to transform this matrix into a matrix that we can solve. Now, we'll be doing a lot more of this coming up, and we can use technology for this, but it's important you know how to do it first by hand, because later, because you've got to do it by hand, because we will have some systems that technology will not work for. So let's quickly run through this process of using elementary row operations to solve this. And this gets us a little ahead of the game for when we dig into this. So as I look at this, there's three things I'm trying to do. I'm trying to get zeros in these three positions. So to do that, the first thing I'm going to do, and again, we'll often remember that first elementary row operation. A lot of times we'll combine that with the scaling one, just out of interest of kind of our own sanity. Plus, it's an easy combination to make. So if I want to eliminate, and I'm going to eliminate not only these three entries, but I want to eliminate them in this order. This one first, then this one, and this one. That way I get a triangle of zeros there that will then lead me to a new, a solvable system. So the way it's going to work is I'm going to, and this is the notation I'm going to use, I'm going to go minus 2 times row 1, add that to row 2, replace row 2. Okay, so that is right on the official first elementary row operation of replacement. We've multiplied one row by a constant, we've added it to another row, and replaced that other row. So over here on the side, I'm just going to do this. It's a minus 2 and a minus 4, a 4 and a 30. It's going to be a 2, a 1, minus 5, minus 21. I'm just copying down the two rows. Going to add them, and there's my 0. That effectively eliminated the x sub 1 variable, or the x term. I will still often, if it's a 2 by 2 or 3 by 3 system, sometimes refer to them as x, y, and z. But that eliminates the x sub 1 variable from this new equation. And there it is. And so then I'll come back in here, and I will enter my replacement, getting the 0 in the first position that I need it to be in. Now, what we have here in this second matrix is if I converted this back to a system of equations, it looks like it looks different, but it's an equivalent system. This is an equivalent matrix because we only applied an elementary row operation. It's an equivalent system. Therefore, the solutions to this second system generated by this equivalent matrix are the same as the solutions to the original system. Okay, so my next goal is to get a 0 right here. And so the way I'm going to do that is I'm going to go ahead and do, let's go negative 1 times row 1 plus row 3, replace row 3. So if we do that, negative 1 times row 1 looks like this. Negative 1, negative 2, 2, 15. Row 3 looks like this. 1, negative 4, 0, excuse me, 1 and 18. And if I did that correctly, I'm going to get that right there. And so I would write that in as my next equivalent matrix. So 1, 2, negative 2, negative 15, 0, negative 3, negative 1, and 9, and then this right here. Right? And that's my next equivalent matrix. I've got the 0 where I've wanted. I've eliminated that x sub 1 term. Now, I'm not committed to that because here's what I want to do to make my life a little easier. I quickly notice that all 4 of those entries are divisible by 3. So I'm going to do another elementary row operation before I commit to putting it in the matrix. Okay? And just to make things easier, and that row operation is going to look like this. It will be basically negative 1/3 times row 3, and that will give me my new row 3. So I'm just multiplying this by negative 1/3, right? Dividing everything by negative 3. And when I do that, 0, 2, negative 1, negative 11, right? And so that just makes it easier. The more I can simplify that, and that's a legal row operation. So I'm allowed to do it. I just didn't want to do that. Didn't want to do that and take up more space. All right, we're going to continue here. It looks like I'm out of my template, so but we'll continue. I now need to get a 0 right there, and so to do that, again, I'm going to do the same replacement row operation, but I need to use the right rows. In this case, I'm going to go 2 times row 2, add that to 3 times row 3. See there, I'm cheating and using a combination of two elementary row operations. Normally, this would not be there, but I'm going to go ahead and use the 3 times that at the same time. And so, let's see, we want to do that over here. So 2 times row 2 looks like this: 0, negative 6, negative 2, and negative 15, or sorry, negative 30. Let me start that one over again. 0, negative 6, 0, negative 6, negative 2, and 18. And row 3 is this, except we want to multiply by 3. This is what happens when you're thinking about the software you're using and what button you're going to push next. So let's back up, make sure we got it correct. 2 times row 2, that looks good. And then a 3 times row 3 is a 0, 6, negative 3, negative 33. And when you do that, you're going to get a 0 like we wanted, a negative 5, and then of course 18 minus 33 is negative 15. So let's do the same thing we did. We notice everything's divisible by negative 5, so we're going to do this. Negative 1/5 times row 3 gives us, and we'll replace row 3. So our system will look like this. Row 1 and 2 are set. But row 3 is now this: 0, 0, 1, and 3. And I've got now my triangle of zeros. All of these matrices in green are equivalent. If I convert them to systems, the systems look different, but the solutions have been unchanged. And so look, if I convert this to a system, it's now going to look like this: x sub 1 plus 2x sub 2 minus 2x sub 3 equals negative 15. Negative 3x sub 2 minus x sub 3 equals 9. And x sub 3 equals 3. And this system can now be solved starting at the bottom, right? That one we've already got. And solving that bottom equation, and then back substituting that answer in there, and then back substituting into there until you have all 3. All right? And that should give you a final solution to the system, which you can check is going to be negative 1, negative 4, and 3. And that is how we solve 3x3 systems, or any system using elementary row operations. So it looks like this particular system has one solution. It's consistent and it is independent. Now, in linear algebra and differential equations, we use the terms existence and uniqueness in reference to solutions of a system. We ask, does a solution exist, is one question, and then the other question we ask is that solution unique? So in this case, the answer to both of those questions is yes. The solution exists, there it is, and it is unique. There is only one. Now, to be honest, these kinds of systems you've got to be able to do by hand, but really these aren't the ones we'll spend a great deal of time with because they're kind of known territory. What we're going to explore is a little bit more about systems that have zero solutions or an infinite number of solutions, but that's all coming up. For now, just make sure you can do this by hand. I know you can do it with technology, but make sure you can do it by hand, because the process itself, there are answers and questions that we can come up with from that process that technology can never give us.